Right, quickly, let's just look at some instruments here. One with both ends open. Okay, say I've got that one. Okay, I can have this happening here. So the reflected wave will come like that. Okay, reflected wave coming like that. Remember that if I were to look at this wave, for example, here, I can say from here 1 up to that point there. Okay, it's half a wavelength. Or let me take it from here. Okay, so from there to there, I've got 1/2 wavelength. Okay, and then from there to there, another half wavelength. So I've got a wavelength from here to there. Okay, or from there to there, I've got a wavelength. Now, this point here where they interfere, you would see when they come together, they give us a point that is bringing us to the rest position, if you like. This is the node. We call that the node. This point here, where we have got this is a standing wave. It's called the antinode. Okay? Right. Now, you can find out how many, if I take it from there to there, this becomes the length of the musical instrument, the L that we spoke about. And then I can find how many standing waves are in here. This is one standing wave, 2, 3, 4. And in fact, I would say 4 because this is a half a standing wave, but together with this one, perhaps I can have the 4th standing wave. Now, standing wave, because you take that as the crest and you can take this as the trough, but because they are together there, we call that a standing wave. All right. Don't have much time to explain everything there. Let me just move on. Say I've got one end closed like that. I can have something like that. Okay, that's a bad one. Okay, let me just quickly check on this one. Say I've got one end open like that. So I can have a wave that goes like that. And then this will be the standing wave like that. And this becomes the length of the musical instrument, L. Okay? Then how many wavelengths do I have here? From there to there. If this was like complete there, I would have had one wavelength. So this is half wavelength. And this would also be 1/2, it will be 1/2 wavelength, and you get those two together. You've got a wavelength in one length. And how many standing waves do you have? That's one standing wave. That's another one. So you've got 2 standing waves there. So your K there would be equal to 2. Okay, so that is more or less what it is with regard to these musical instruments. And now quickly coming to Doppler effect. Let's have a look at this question here. A train approaches a station at a constant speed of 20 meters per second with its whistle blowing at a frequency of 458 Hertz. So source moving towards listener here. Okay, so we expect the frequency heard by the listener to be greater than the frequency of the source. An observer standing on the platform hears a change in pitch as the train approaches him. It passes him and moves away from him. Remember, pitch is what? Frequency of sound. Okay. Now, name the phenomenon that explains this change in pitch. Now, this is straightforward. You should be able to say this is Doppler effect. Okay, This is Doppler effect. Now, this is an exam question. I took this from a previous question paper. So this is how you are going to be asked questions based on Doppler effect. The next one says, calculate the frequency of the sound that the observer hears while the train is approaching him. Use the speed of sound to be 340 meters per second. Now remember, with the source approaching, the frequency of the listener is going to be V divided by V minus V source times what? The frequency of the source. And all you need to do at this point is to start substituting into it. V is what? 340 divided by V is also 340 minus the velocity of the source, the velocity of the train is 20 times the frequency of the source, frequency of the train of the whistle by the train. I think is 458. We can confirm that quickly. Okay, so 458 hertz. So that's what you have. And when you have done this, you get the answer. I'm going to finish off this when we come back.